Hello, everyone. Welcome to another meeting of our conversational AI reading group. Today, we are very excited to have a great speaker, Marc Delcroix from NTT Communication Science Laboratories, talking about neural target speech and sound extraction. If you have any question during the talk, feel free to post them in the chat or raise your hand to ask your question. Without any further delay, the stage is all yours.
Thank you very much for the introduction. I'm Marc Delcroix from NTT, and I will present about neural target speech and sound extraction. As Pony mentioned, if you have some short questions, you can ask them during the talk by the chat, I think. I will have like two parts in the talk. So if you want to have a bit more longer questions, I will also leave some room for questions at that time and after the talk also. So. So in the talk, I will introduce the problem, and then I will actually, as the title mentioned, just speak about the target speech extraction and then the target sound extraction in part 1 and 2. So first, I want to acknowledge this work is done with many collaborators. Most of them are listed here, and it's past colleagues, interns, etc. And yeah. So what is this talk is going to be about? It's about kind of selective hearing. And in our everyday life, we are often in situation where maybe several people speak, like in the picture here, or there may be some phone ringing or something. And we human, we can usually focus our attention on a specific person, for example, or on a specific sound. And this is what we call selective hearing. And we can do that by using different clues, for example, the location clues, because we have two ears, we can focus on attention on a specific direction. It can be the voice characteristics or the sound characteristics of the sound we want to listen to. There can be some visual clues, some semantic clues. And because of that, we can actually, for example, follow a conversation in a cocktail party. And if someone, for example, says our name in a conversation, we can switch our attention to that. Or if a phone starts ringing, we can switch our attention to that too. So we find that this is a very important capability of humans. And the goal of this work was to actually realize computationally such a selective hearing. So we reformulate the problem as extracting the signal of a target speaker or a desired sound in a mixture, given clues about the target. So to show you here the example of the speech extraction is we would have a situation where we have, for example, two speakers and maybe some noise that is captured by a microphone. So at the microphone, we observe a mixture of speech. And the target speech extraction, the TSE system, will extract from this mixture only the signal we want to listen to, the target speaker signal. And how we define the target is by giving a clue about who is the speaker we want to listen to the system. And this clue can be and will be in this talk basically a short recording that captures the voice of the target speaker, from which we can get the voice characteristics of the target speaker. So by informing the system about the voice characteristics, we will be able to select who is the target speaker, extract this voice, and ignore all the interference and the noise. And there is a related problem, which is the target sound extraction, which is basically the same ideas. The only difference is that instead of dealing with speech signals, we deal with arbitrary sounds like telephone, dog barking, and stuff like that. And we can just select what kind of sound we want to listen. In this case, for example, we say we want to extract the telephone, and then from a mixture of the different sounds, we would output only the signal of the telephone. So this kind of technology may have many applications. For example, for speech enhancement, we can embed this technology for hearing aids, hearables, teleconferences, or voice recorders so that we can better listen to the important or desired speakers and ignore the interferences. We can also use such technology as a front end, for example, for ASR, for speech recognition. And This may enable, for example, a smartphone or a smart speaker that can focus on the voice of the user and not the other people's voice, even if someone is interrupting the command, for example. And for sound extraction, we can think that, for example, if we record a video or something and we want to emphasize some kind of sound, we can use that for sound post-production or remixing. And also we can also use that for hearables. So, for example, if you are in the street, maybe there are some sound like sirens that we are very important to be able to listen to, but some other sound we want to remove. So we can have a smart kind of more smarter hearables. Okay, so that's for the problem, and now I will jump into the first part, which will be about target speech extraction. And here, I will first explain a bit the difference between separation and target speech extraction, because separation is very related to the problem. Then I will explain how we started working on this problem, like explain a bit the basis. So it's quite simple idea. So I want to explain a little bit how we started and explain a little bit about the speaker beam framework. And then I will briefly show like a video of a more recent achievement, which is a diffusion model-based TSE. Okay, so first, let's start with explaining a little bit the relationship with separation and the difference. Mm. So speech separation consists of given a speech mixture. Here we have two speakers. We have a speech separation system. So typically in this case would be a neural network that will be trained to separate the input signal, the input mixture, into all of its sources signal. So in this case we have two speakers. So there would be two outputs. So this is very useful and very nice technology, and it has many applications, and lots of research is done in this direction. But in the case of target speech extraction, there are two limitations that I want to emphasize. Is that typically when we do separation, we need to know or estimate the number of sources, because the number of outputs will correspond to the number of sources. And estimating this number of sources in practice is not always easy. So this is one potential issue. And the other issue is that if we're actually interested in one specific speaker, the separation will give us two signals, but at the output, there is an ambiguity between the source and the output. We don't know which outputs correspond to which speaker. So if we want to actually, we're interested only in one speaker, or we want to have the identity, the signal associated to a specific speaker, we need to combine the separation with some kind of speaker identification system. And if we combine these two systems, of course, there will be always some errors that may cause error propagation, that may actually cause actually to, for example, select the wrong output as the target speaker. So um, these are two limitations from the separation system that are addressed by using the target speech extraction. And basically, the target speech extraction focuses only extracting the target speaker. So it's perform the speech separation and speaker identification at once. So by exploiting the target clues, so that's a big difference between the separation, is that we require to have some clues about the target speaker, but by having this clue, we can avoid the limitation of the separation scheme, which means that because we have only one output which corresponds to the target, we don't need anymore to estimate the number of sources. In principle, the signal can have as many sources, the output will be only one target source. So it's more flexible in this sense. And also, since the output signal is always should be the target source, there is no source output ambiguity. Okay, so this we were interested in doing something like targets speech extraction, and this idea started in our lab in 2016, and I want to explain how we designed the system at that time. So first, at that time, so it's around 2015, so it's already 10 years ago. So maybe many people don't know, don't remember the situation at that time. But at that time, um, uh, like there were lots of work on speech enhancement using DNN. And at that time, what the major approach was to try to use a neural network to estimate a time frequency mask. So we would have the mixture, which would consist here of speech and noise. And the neural network would be trained to estimate for each time frequency whether the speech was dominant over the noise or otherwise. So then we get this kind of mask, and by applying this time frequency mask, we could remove the noise. And it's actually quite easy to train such a neural network by using simulated data because it's quite easy because the speech characteristics and the noise characteristics usually are quite different. So the neural network can learn pretty well to discriminate these two types of signals. And this approach was very promising by when it was combined with beamforming. So it's what we called a mask-based beamformer. So the neural network will use a single channel to estimate the mask, and then this will be used to design a beamformer to extract, to enhance the speech from one direction. So that was used, for example, in the Chime 3 workshop. So but this problem is actually speech and noise, but we are interested in the problem where we can discriminate between two speakers. So in this case, if we have two speech signals, what we would like to have is a mask that indicate where the target speech is present, so it's dominant over the interference speaker and the noise. But the problem now is how can we identify the target? And it's actually difficult to, if we don't have any clue, it's difficult to learn such a, or impossible to learn such a neural network because it's two speech signals. So it's the network by itself cannot say who is the target, who is the interference without any clue. So the solution at the time were actually two types of solutions. The first solution was to have a speaker-dependent system. So you would train one neural network for a specific speaker. And if you have a different test speaker, you need to have train a new neural network for that speaker. So it requires quite a lot of data and one model per speaker. So it's pretty heavy and not very flexible. The other approach is to say we don't have a clue, but we know that the clue is implicit. So we would extract, for example, the speaker that is dominant, so the louder speaker, for example. Or for example, if you have a male-female mixture, we would always extract the female speaker or always the male speaker, for example. So in this case, we can have some kind of bias that tells us what should be the target. But as you can imagine, this is also not very generalizable because sometimes it's not easy to say which one is the dominant speaker. Sometimes you may have two male speakers in the mixture. So how do you deal with such situations? So our idea was whether we could use such kind of system, but adapt using model adaptation to adapt it to the speech, the target speaker we want to extract so that it can extract that speaker and ignore the interference. And this idea of using adaptation actually comes from ASR. And at that time, we were doing some work on acoustic model adaptation. So briefly, the typical ASR system at that time was consisted of having, in this case, it's a single speaker, a clean speech. We would have a feature extraction, an acoustic model, so typically a DNN HMM hybrid system, and then a language model that will output the word sequence. So in this case, the acoustic model was trained on many speakers, but it's generally not optimal for a given speaker. So one technique that was widely used is to use speaker adaptation. And one way to do the speaker adaptation is to compute a speaker embedding, which typically is a I vector, and add this I vector to the acoustic model. So the acoustic model could kind of um, fit better to the speaker voice characteristics. And even though it's a single speaker, this adaptation to the target speaker, to the speaker voice characteristics, would actually improve a little bit the ASR performance, and was therefore quite a popular technique at the time. But again, here, in this case, it's mostly for ASR, and it's actually also dealing only with a single speaker and just adapting the model to that speaker characteristics. There is no notion of speech mixture in this case. But we borrowed this idea and try to apply it for realizing the target speech extraction. So how we did that is that we decided to assume that we have some enrollment about the target speaker. So typically, for example, 10 seconds of the speech of the target speaker. And from that speaker, from that speech, we would extract the speaker embedding and use this embedding to adapt the neural network, the enhancement neural network, so that now it can know who is the target and who is the interference, and it can therefore predict such kind of mask to extract only the target speaker and ignore the interference. So simply by adding this speaker embedding, the neural network it become conditioned on the voice characteristic of the target speaker so that it can realize target speech extraction. So that's the very simple idea to combine the kind of speech enhancement and ASR adaptation techniques to realize target speech extraction. So as you can imagine, now we can have actually a model that is adapted to a specific speaker using only, for example, 10 seconds of speech. So it's become much more flexible. We don't need to have a specific model for each speaker. We just need to, at test time, have 10 seconds of speech of that speaker so that we can do the extraction. So initially, we actually investigated different ways of performing the conditioning and different ways of computing the embedding vector. So here, briefly, there's three different options for the conditioning. So the simple way is this lambda here represent the embedding, the speaker embedding vector. The simple way is simply to add this embedding by concatenating it to the input of the neural network. A more sophisticated approach is to use some kind of factorized layer. So this is the kind of is similar to kind of a mixture of expert kind of model. And I was actually doing research on that for ASR. So this is why we started using this architecture at that time. But then also there were actually a simpler way to do adaptation for ASR, which is simply multiplication. So we have some layer of the extraction network, and for intermediate representation, we just multiply it with the embedding, and this also a way to do the conditioning. Of course, you can do addition too. You can now there's been film or some kind of attention approaches can also be used, but at that time we use compare these approaches. And for the speaker representation, we tried several options. So the first one was to use speaker posteriors, but actually we quickly abandoned this idea because it was not very good for unseen speaker conditions. So when the speaker was not seen during training. Then we also tried using I vectors. And another option was to jointly train the embedding extractor with the extraction. So we had actually a small neural network that the goal was to extract the speaker embedding. And this was randomly initialized and learned jointly with the extraction network. And so again, this is quite old result here. So for now, that people that are working on speech separation, these numbers look very bad. But at the time, this preliminary experiment showed that actually you could do extraction. You have a SDI improvement of about 6 dB. So you could emphasize the target speaker. And we show that the factorized layer with a jointly trained embedding was actually the best solution, but it's actually a bit heavy in terms of computations. So instead, the multiplicative conditioning and also jointly learned embeddings provided quite also good performance. So this is actually the approach we mostly used. And as for the speech enhancement, we could combine this framework with a beamforming. So this is what we call the initial approach of speaker beam. So we have for each channel, we perform the target speech extraction to estimate the mask for extracting the source. And from that, we can compute a spatial covariance matrix and design a beamformer to enhance the signal. So I will play you a video here to show you what was the performance at the time. Okay, so in this demo, first we record the voice of the target speaker. So in this case, I'm the target speaker.
We first record 1 or 2 sentences containing only the target speaker's voice. We then use this recording to obtain the characteristics of his voice.
And then we will extract my voice, and there's two scenarios. The first scenario will be like one mixture of one male and one female speakers, as like this.
Speaker beam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people. Speaker beam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people.
And the next demo is male and female, two male speakers, and also background music.
Speaker beam focuses on the voice of the target speaker. Even if there is music playing in the background, or if someone jumps in the conversation like this, you can keep listening to the voice of the target speaker without being disturbed. Speaker beam focuses on the voice of the target speaker. Even if there is music playing in the background, or if someone jumps in the conversation like this, you can keep listening to the voice of the target speaker without being disturbed.
Okay, so I hope you could perceive that the voice was extracted. So of course you can still listen a little bit to the interference speaker. So it's actually doing beamforming. So it's not completely removing. I mean, there can be some remaining signal from the, for example, for the reverberation of the interference speaker and so, but quite you can see that the target speaker is pretty emphasized. And this was actually a demo we realized in 2018, so it's already a bit old. But yeah, to summarize, actually it's quite easy to build a TSC system if you have a speech separation system. So if you have a toolkit for speech separation, like that has a neural network speech separation approach, I will show you how you can kind of implement a TSC system. So the typical speech separation you would have as an input speech mixture, you would have some processing blocks. So that's the design of the network is changing very quickly. So now maybe you would have like TF-GridNet or something like that. And then at the output, you would have two output, one for each source. And this would be trained with many simulated mixtures. And also for training that, you would use a permutation invariant training loss, which will compute the minimum between the permutation between the estimated signals and the true references. So assuming that the first output correspond to the reference x1 and the second output correspond to the reference x2, or the permutation case, we take the minimum of the two. So this is the PIT. So if assume that we have such a system, like the code for training such a system, for example, how can we make a TSC system? Is we can use basically similar kind of architecture for the processing. First thing we do is we add as the input this enrollment. And for training, typically we would sample another utterance from the speaker in the mixture, so not the same utterance, but simply randomly select another one from the dataset. Then the next thing is that we need to add a speaker embedding extraction module. So this can be some kind of a speaker embedding you would have, some X vector or something, a kappa TDNN or anything. But you can also make a simple neural network and you can learn it jointly with doing the training. Then the next thing to do is to add the fusion layer. So that's what I showed in the previous slide. It can be complicated like a factorized layer or simply kind of a multiplication of the embedding and the input of the fusion layer. Then you have to modify the output. So instead of having multiple outputs, you simplify it to have only a single output that corresponds to the target speech. And you also can simplify the loss. Instead of having to compute the permutation, you always know what is the reference, so you can have a much simpler loss. So that's how you can do. So it's very easy to implement. And for example, at the time we use, for example, the Conversational architecture and simply added this multiplication layer inside and added this speaker embedding, and we compare the performance with the Conversational at the time. So here we have, in blue, we have the separation with Oracle speaker identification. And then in blue here, we have the separation when we also identify the target using X vector. We can see that we have quite some degradation in this case. Because the separation is not perfect, we would have error in the identification. And then the light red one is when we do a speaker beam with a frequency domain with a mask estimation. And the red one is the time domain speaker beam. We can see that we have actually a similar or a little bit better performance than separation with Oracle identification. So this idea is quite simple, as I mentioned, and therefore we can apply it for a more complex model. For example, recently diffusion model have been used, as you know, for many tasks and also for speech enhancement. So we also try to extend diffusion model-based speech enhancement to perform a TSE, so diffusion-based TSE. And this is done by conditioning the speech distribution on not only the mixture, but also the clue, so the target speaker clue. And I won't go into the detail, but I want to show you just a video. So this video, actually, the recordings is in Japanese, but I still think you can get the sound extraction. So, but the big difference is that now we use a much more powerful model, the diffusion model, and we can realize actually quite good extraction using a single microphone. The previous video was using 8 microphones, but now even with a single microphone, we have quite a good recognition, quite good extraction without too much distortion. So yeah, so this is the single microphone used to record the two people's voice.
今回の実験結果、前回と比べてだいぶ安定してきましたね。コードの再現性が若干不安定で、今ログを追って調査しています。今回の実験結果、前回と比べてだいぶ安定してきましたね。コードの再現。
データの分布に偏りがあるので、正規化する必要がありそうです。
So even with a single microphone, we could have quite a good sound quality. I will wrap up this first part of the talk. So I think I explained the idea of the TSE, and it can be realized quite easily by conditioning a neural network on the speaker embedding. So it's a simple idea, it's quite practical. So we started the investigation in 2017 and proposed speaker beam. So quite early, there was some follow-up work, for example, deep extraction network, voice filter, etc. And now actually there are quite many papers related, um, like from ICASP and Interspeech, like this year, about 30 papers were presented. And so now I only presented using the audio clue, like the enrollment to do the extraction, but actually it's related to other modalities. For example, you can use the visual, the lips of the speaker to do the extraction. Some people try to use EEG, so the brain signals. And there's other clues that you can imagine, like speaker activity, semantic clues, etc. And also here I focused on the extraction of the signal. So you can listen to actually the extracted signal, but actually you can also use a similar ID for slightly different problems. For example, by simply conditioning the ASR system on the target speaker embeddings, you can realize target speaker ASR. So this does not require to perform the extraction and then the recognition, but you can do it at once. So it can be quite efficient because the conditioning, as you've seen, is simply adding some small modification of, for example, ASR encoder. So in terms of computation, it's almost the same as a normal ASR system, but it can handle a multiple speaker and ignore the interference. And there are some people doing also a personalized VAD or target speaker VAD. And the next thing I will explain is about target sound extraction. So I think now may be a good time if you have questions for this part of the talk.
Yep. Is there any questions? Please raise your hand or drop the question in the chat. So maybe I have one question. So all of the systems that you describe could handle two speakers. So if you want to extend to multi-speaker, how does it work?
So basically, yeah, the idea here was we only focus on one speaker in the mixture. So if you want to have another speaker, what you would do is simpler way is just to process twice for each of the speaker. So that you can do. You can also imagine to have a bit more sophisticated approach where you could pass directly several clues and get two speakers output. And actually, we didn't do that for the speech, but for the sound extraction, we also experimented extracting a mixture of two sources. So for example, if you have like three sources, but you still want to listen to two sources, you don't separate the source, but you output the mixture of the two sources and remove one of the sources. So that's also possible. Yeah.
Okay, perfect. So I think we have two questions from, so Sam, do you want to just go ahead?
Yes. So, did you try did you compare the performance between like just applying a speech separation or source separation system, like extracting all the sources and then somehow identifying like the source versus the targeted, like this
Yes.
type of target extraction?
Yes. So this is actually this is one example of that. We tried several times. This is one of these examples. So this light blue would be actually the separation. And in the separation, usually when you do separation, when you do the evaluation, you do the oracle permutation of the speakers, right? So that's actually the upper performance for target speech extraction. So if on top of that you do some identification, so that would be, in this case, it's using X vector. It's actually not optimal because we didn't train the X vector on the process signal. So you can argue that it could be a bit better, but we have some degradation. And then this is the target speech extraction. So of course, this is a bit old data. If you know these numbers goes to, depending on the data set, almost to 20 dB sometimes.
Yeah.
So in this case, I'm sure you get actually a slight, maybe less degradation. So definitely it's not always the case that you would get better performance, but it's actually quite simpler system, I would say.
I see. All right. Thank you, Mark.
You're welcome.
Okay, thank you. Mirko, do you want to ask the question?
Yeah, just a curiosity, actually. If I remember correctly, you said that there are applications of this also on EEG, right?
Yes.
Can you comment a little bit more on that? Because I think it's very interesting, that part.
Yes, so it's not our work, so I cannot talk too much about the details, but it's basically you can from the EEG you can kind of predict the envelope of the signal, which is the people is listening to, is focusing the attention to, and from that you can use that as a clue to kind of extract from the mixture that signal, so it can emphasize the speaker the people are willing to listen to. So I think it's still pretty. I didn't follow the recent development, but I think it's still pretty kind of maybe not completely practical yet. It's very early research, I think, but yeah, there is quite interesting work in that direction, I think.
Yeah, very cool. Thank you.
So maybe for that, yeah, there's this work in 2020 was one of it, and I'm sure now there's much more, but yeah.
Okay, there are more questions in the chat. Do you prefer to answer them now or at the end of the talk?
It's up to you. If you feel that the question is very related to this part of the talk, then I can answer now, but otherwise, yeah.
Maybe there's one specific question that you could answer, and then we could keep the rest for the end. Which causal TSE architecture meet the 5 to 10 millisecond latency constraint requiring for hearing aids?
Okay. So yeah, that's a very good comment. So in our work here, we actually don't deal with causal. In what I'm presenting here is not causal. Is everything is offline. But yeah, there are some work that actually do causal extraction. For example, one example actually, if you're interested in that kind of work, is the coming Chime 9 challenge has one track related to TSC, and it's about actually recorded by hearing aids. And I forgot the requirement is maybe it's not 10 milliseconds, maybe they relax it to 30 milliseconds. But and in this case, the baseline is basically using kind of TF GridNet kind of architecture and adding the conditioning on the target speaker. Yeah.
Okay,
I'm not sure if I answered the question.
So maybe we could keep all the questions for the end for now. Maybe we could continue and then we will have another Q&A at the end.
Okay, sure. So now the next part will be about the target sound extraction. So the idea here is that sometimes when a same sound can be considered as noise in some environment, but in different environment, the same sound can carry very important information. So for example, if you work at home and there is a siren outside, this is a kind of noise that will disturb you. But if you drive your car and you have a siren, it's very important to know that you have to drive on the side. So we want to actually make a system that can you can select what kind of sound you can hear and what kind of sound you can ignore, for example. And so this is actually very similar to the target speech extraction I'll just explain, but instead of doing with speech signals, we deal with other sound signal, arbitrary sound signals. So in one aspect, you can think that speech signals have very similar characteristic, frequency characteristics. So it's more difficult to discriminate than arbitrary sounds that may sound very different. So the network should it should be easier for the network to learn to discriminate these different sounds. So it may make the problem easier, but at the same time, you are dealing with a large variety of different target sounds possible. And also in practice, it's maybe not easy to define all the target sounds at once. So you may need to actually add new sounds to the system as you use it, because for example, a new type of phone siren comes up or something, or a sound ring comes up or something. So this maybe require continuous learning. So you can see that this target sound extraction is quite challenging too, I would say. So just to recap, it's basically using the similar ID as the target speech extraction. So we would have basically a neural network that have as an input a mixture of different sounds, and we also have a clue. And from the clue, we have some clue encoder that will extract the characteristics of the target sound. I will discuss after what kind of clue we can use. And the sound extraction network will be extracting from the mixture the sounds that match the characteristics of the target of the clue. And then the output is only the target target sound. So there have been investigation on this work about many different clues, but basically mostly we can see two types of clues. One is to use a one-hot vector to characterize the type of sound we want to extract. So for example, if we would have we want to extract the phone, we have like the second position on the one-hot vector correspond to the phone class, and all the rest is zeros. And using that, we can have as a clue encoder, we can have simply an embedding matrix that will map this one hot to embedding vector. So, and then we can do the extraction by conditioning on this embedding vector, the sound extraction network. So this extraction is via sound class labels. And when we train such a system, we can directly optimize the embedding for a sound class. So that's a nice property. But one limitation of this approach is that we can only extract the sounds that we have seen during training. So the type of sound and the number of sounds will be fixed by this one hot vector, and any new sounds cannot be dealt with. The other approach to do the sound extraction is to use a similar approach as the speech extraction. So using an enrollment, so some audio sample of a sound similar to the sound we want to extract in the mixture. And then we can, from this audio signal, we can compute embedding that represent the sound and also do the extraction. So this extraction is done, we can say, via sound similarity, looking at whether the sound in the mixture looks similar to the sound in the enrollment. So there is no kind of explicit notion of class here. So in principle, it can generalize to new sounds. So even if it's a sound that has not been seen during training, but you have an audio recording of that sound, it may be able to extract it. But we don't actually directly optimize for any sound class anymore, so the embedding may not be optimal. And actually, we observe usually that the enrollment-based approach perform a bit worse than the one-hot-based approach in our experiments. So what we thought is, could we combine these two approach to combine the advantage of both frameworks? And this is what we proposed in the SoundBeam framework, and is basically we can see that we can use the same sound extraction network, but use different clue encoders. And by learning this kind of system, by alternating between the two types of encoder, we can learn the sound extraction. And this can be done with some kind of multitask learning. So we would do the extraction using, for example, the enrollment and compute the embeddings and condition on this embedding and do the extraction. Or we can do the same, exactly process the same mixture, but using the one hot. And if we use the same sound extraction network, but we need to alternate between these embeddings. That means that we enforce that these two clue encoders will generate embeddings that map a common embedding space, that will map to a common embedding space. So this is what is shown here with this TNAC plot. If you see the color plots, it's the color dots is actually some samples using the audio enrollment. And inside we have a small black dot, and that's the one obtained with the one hot encoder. So we can see that basically they match pretty well in the embedding space. So we can now use extraction using either the enrollment or the one hot. So what is the advantage of doing that? First, simply by doing such kind of multitask learning, we typically improve the performance. So that's a side effect, which is nice. And we can actually obtain nice performance using the one hot encoder, which can get optimal embeddings for scene classes. But at the same time, if we want to extract unseen classes, we can use now the enrollment encoder. So we combine the advantages of both approaches. But we want to go a little bit further. So even though we can extract new classes, we thought that maybe we could actually try to augment the one hot encoder for new classes. So the idea is that, for example, if the TSC system was not trained to extract cat sounds, can we add a new class, the cat sound classes, to a TSC system without retraining everything and with having only a few samples of cat sounds? So basically, from the one hot embedding matrix, we would add a new column for the new sound, and with a few sound samples, we will retrain these embeddings and fix everything else so that we don't change the behavior for the other classes. So to put it a bit more concretely, so first we assume we have a few enrollment samples as shown here. I don't know, maybe you see better here. We have here a few enrollment, and we fix the parameters of everything, but we add here to the embedding matrix, we add a new column for the new class. And these are the only parameters that we will learn. And first, we can initialize these parameters. And how we do that is we have here a few audio samples. So for each of these, we can compute the sound embedding using the enrollment encoder. And we can do the average of these K audio samples embeddings and to get the initial value for this new class. And then we generate a few mixture using only these K audio samples and some other sounds. We generate some mixtures and backprop and optimize only this embedding so that it becomes optimal for the extraction of the new sound class. And even though we do the backpropagation, since we fix everything else, for all the previously learned class, we don't forget anything. So we can allow to have continuous learning, learn new classes without any catastrophic forgetting. So to show you some results, so here it's an example of an experiment where we have a mixture from 41 different sounds taken from FSD 50K. And this gray line here is an example of a sound separation system. And again, using Oracle sound selection, we have about 11 dB SDR improvement. And this is the same system, but when we do sound classification to select the target sound. So we see quite a big drop in performance. And then these two blue lines are the TSC, the target sound extraction, using the enrollment and the one hot. So we can see the one hot is a little bit better, and both are actually quite better than using the estimated sound classification. And then the sound beam using the multitask learning, only using the multitask learning effect, we can improve slightly the performance. Now, what is more interesting is that if we consider now 20 new sound classes, so 20 sound classes that have not been seen during the training. So now, using the enrollment-based encoder from Soundbeam, we can already extract these sounds, like if you use the enrollment-based TSE system. But on top of that, if we perform a few-shot adaptation, we can see that for the scene classes, because we fix all the parameters, we keep exactly the same performance. But for the unseen, the experiment with unseen classes, we have actually performance improvement from about more than 1 dB. So we can actually improve performance and learn a new class with a few-shot adaptation. And I will show you a video so you can see what is the target sound extraction doing. So this is a video where I recorded some sounds at the office. Sorry. So first we listen to the recorded mixture. So, and we extract one sound at a time. So computer keyboard. Then cough. Okay, and I think I will stop here. So I just want to wrap up and say that, okay, we can extend the idea of target speech extraction to arbitrary sounds. And we also introduce a framework for continuously learning new sound classes. So there are actually many remaining work direction in this kind of project. So there are some works trying to make the system lightweight and online processing, and also further improving the performance. For example, we have a recent work where we try to use a sound SSL model to boost the performance. And also, there are many works trying to use different clues. For example, sound description, like linguistic cues to describe the sound, is also very many works are targeting that. So yeah, that will conclude my talk. Thank you for your attention. If you want, we had some overview paper on target speech extraction. So in this presentation, I focused mostly on our work, but this one is a bit more general. And so if you're interested, yeah, have a look, and otherwise I'm happy to answer questions.
Thanks for the great talk. So I think we have a bunch of questions. I also want to ask one question myself. In the target speech extraction, you basically pass a speech target as an input. So what is the effect of selecting the right target sample? For example, does the performance improve when the chosen target speaker match the prosody content or, I don't know, emotion of the inputs that we pass or not?
Yeah, that's actually a very good point. So, of course, if you, for example, if you have exactly the same, you cheat and you know the speech that is exactly the same in the mixture, this is kind of maybe optimal performance, I would say. You maybe get a little bit better. So then, one thing we actually looked in a work I didn't mention here, but we looked actually at the influence of emotions on the target speech extraction. And we see that actually depending on the mismatch between the emotion in the mixture and in the target, sometimes the performance can degrade quite a lot. But actually, interestingly, we found that in our case, if we use quite neutral embedding, then the performance is quite good for any emotion in the mixture. So
Yes,
yeah.
Okay, perfect. So there are some questions in the chat. What kind of metric do you use for target speech extraction? What are your thoughts about the over suppression metric and the over suppression losses from the voice filter?
Okay, so in most of this, I use simply the SDR to evaluate, and I'm sure I'm very aware that SDR is not best metric, but this is a simple metric, I would say. So I'm not completely sure what you want to say about over suppression. Um, so I'm not completely sure if I answer completely right. So I think here one issue we also looked in the evaluation, but I didn't mention it here, is that one aspect that we want to check is if the target is not active, we want to extract nothing. Because ideally the system should be able to recognize if the target speaker is present or not, and if the target speaker is not present, it shouldn't output anything. But if you actually naively train the system only seeing active mixture, so if the speaker is always active when you train it, basically what it does is learns to extract anything that is close to the target speech or target source, and therefore even if the speech is not active, it may actually output something, uh, try to output something anyway. So there is some ways to mitigate this problem, and it's actually also something that is interesting to measure is whether actually the system can kind of correctly find out if the target source is not active. I don't know if I answer the question actually.
Okay, there's one question for TSE. Can you comment on the robustness of conditioning the DNN with a speaker embedding if the target changed voices, for example, speaking loud, changing pitch, or etc.? And maybe follow-up question that maybe you could answer is what are the best research direction to take in the broad field of speech enhancement in 2025?
That's a big question. So so the first question is mostly I would say it's related. Well, the most thing I can say is related to what I told you about the emotion. So this is one of the aspects where we actually looked at the influence of the voice change. And yeah, I can say that depending on the mismatch between the enrollment and the mixture, there may be an impact and performance may degrade. So this may be an issue. And the second question is a bit too broad to address, I would say, but I think there's interesting directions. So, for example, for speech enhancement, the urgent challenge, for example, is trying to design kind of a universal speech enhancement system, so that can handle many different distortions, a same model that can handle many distortions, and also, for example, packet loss and wind noise and stuff like that, and also the noise stereo vibration and stuff like that. So this is kind of interesting, and also many there's important to do much more work on trying to get very high performance, but with low latency, and this may be also important directions. I don't know if, again, I'm not sure I'm good at answering these questions. Just forgive me, it's getting late here, so this may be, let's put it on the time.
Yeah.
Any other questions?
I think that we're done with all the questions. Thanks a lot, especially for staying that late in the night. I know it's too late for you.
I just wanted to say that if my answer is not good, you can just pretend it's just because it's late.
No, they were good. Thank you, Marc.
Okay, thanks.
Thank you. Thank you, everyone, for joining. Next week, we have Juan Rafael talking about multimodal analysis of Parkinson's disease symptoms. And thank you, everyone, for joining. Looking forward to meeting you all next week.